When you look at a modern chatbot, you see fluid, coherent thoughts pouring down the screen. It feels like watching an entity formulate a complete idea and then type it out. The software driving that interaction is a GPT, a generative pre-trained transformer. The first word tells us its function. It generates new text. The last word points to the specific neural network architecture making it possible. But that machine is not generating paragraphs or even sentences. It is generating exactly one tiny chunk of text at a time. For every single word it produces, the model calculates a massive probability distribution across tens of thousands of options, selecting a single winner based entirely on what is statistically most likely to follow your prompt. Here is the central engineering problem. Human language is discrete. We communicate in distinct, isolated symbols. Machine learning, however, requires continuous geometry. It only functions through fluid mathematical operations. To bridge that gap, a network must first translate our discrete words into exact spatial coordinates. Understanding how an AI predicts the future requires understanding how it turns language into geometry. At its core, a transformer is a highly organized sequence of matrix vector multiplications. To survive this environment, all incoming information must be formatted as an array of real numbers, often referred to in deep learning as a tensor. Gray arrays represent the data, your specific input text. The blue and red grids are the weight matrices. These weights, 175 billion learned parameters, are permanently locked. The gray data dynamically flows through them, multiplying against the weights and updating numbers at every layer. There are deeply complex operations buried in the middle of this pipeline, specifically the attention blocks, but we are going to bypass those for now. To demystify how matrices process human language, you must track the exact moment the data enters the network and the exact moment it exits. The pipeline begins by fracturing your input text into tiny, manageable pieces called tokens. Think of them as individual words or small fragments of words. The model references a strict, predefined vocabulary. For GPT-3, this is a rigid list of exactly 50,257 possible tokens. The text hits the first major parameter block, the embedding matrix, or WE. Every word maps to one specific column. Type tower, and the model plucks out the corresponding column. That column is massive, exactly 12,288 individual numbers. The embedding matrix acts as a dictionary, but instead of providing definitions, it translates discrete human symbols into precise, high-dimensional machine coordinates. Those 12,000 numbers are not random digits. They act as spatial coordinates, plotting the word inside a vast, multidimensional arena. This creates a geometric space where words with similar contexts naturally settle into the same neighborhood. Tower lands physically close to skyscraper and spire. Because words are physical locations, distance and direction encode semantic relationships. Take the vector connecting man to woman. Slide that same arrow over to king, and the tip points directly to queen. Direction itself encodes gender. During training, the model absorbed incredibly specific historical patterns and mapped them geometrically. If you take the spatial coordinate for Italy and you mathematically subtract the coordinate for Germany, and then add the embedding vector for Adolf Hitler, the resulting math points directly to the coordinates for Benito Mussolini. The machine completely lacks a biological understanding of history or language. It possesses only a flawless, multidimensional map of how human concepts relate in space. So, how does a computer actually measure the distance and relationship between thousands of spatial concepts using basic arithmetic? It uses the dot product. You multiply corresponding components of two vectors and add the results. Geometrically, this measures alignment. Vectors pointing together give a positive number. Perpendicular is 0. Opposite is negative. You can isolate specific semantic traits this way. If you subtract the word cat from cats, you isolate a spatial direction that represents plurality. Compute the dot product of that specific plurality vector against other random words, and plural nouns consistently yield higher positive numbers than singular nouns. Matrix multiplication is essentially a massive, automated pile of dot products. At every layer, the network is constantly filtering and measuring the geometric alignment of your text against its learned parameters. When an embedding vector first drops out of that initial dictionary matrix, it is completely isolated. The vector for king only knows the generic definition of king. As that vector moves through the black box of the internal network, it passes through attention blocks. These allow the individual word vectors to talk to each other, mathematically tugging and pulling the coordinate based on the surrounding sentence. Say the final word in your prompt is professor, and the preceding paragraphs are heavily loaded with phrases like Harry Potter and least favorite teacher. By the time that professor vector reaches the end of the internal network, it has been pulled into a specific, context-rich coordinate point that heavily implies the word Snape. Out of the thousands of vectors flowing through the sequence, the model relies solely on the very last vector in line to predict what comes next. That final coordinate enters the unembedding matrix, or WU. This operation reverses the initial process, mapping the 12,000 dimensional coordinate back against the 50,000 words in the vocabulary. The output is a list of 50,000 raw numbers called logits. Each one represents a specific score for every single word that could possibly come next. The network has successfully translated the geometry back into vocabulary. But these raw logits are mathematically wild and entirely useless for making a clean statistical prediction. Raw logits are chaotic. Many of the values are deeply negative, and if you add them all up, they do not equal 1. They do not form a valid probability distribution. This chart displays a sample of those raw logit scores. To turn this mess into actionable statistics, the network uses the softmax function. First, it raises e to the power of each logit. This forces every negative value above the zero line. Because it uses an exponent, the baseline differences are aggressively magnified. Large numbers separate dramatically from the pack. Next, it divides each term by the total sum. The entire chart compresses cleanly into a scale strictly between 0 and 1. Now all values add up to exactly 100%. The highest original logit naturally dominates the new distribution, commanding the vast majority of the probability. Softmax is the essential mathematical bridge. It forces the boundless, arbitrary outputs of matrix multiplication into a strict, readable statistical format. Before the computer pulls a word from that finalized distribution, engineers have the ability to manually warp the odds using a setting called temperature. Mechanically, temperature is a constant value divided into the exponent of the softmax equation. If you drag the temperature down towards 0, the function becomes hyper-aggressive. The single most likely word spikes, hoarding nearly all probability and crushing the alternatives. At low temperatures, the model becomes rigid, consistently picking the exact same predictable word every time. If you dial the temperature up, the math flattens the chart. The top choice loses ground, and less likely options gain enough weight to be selected. Temperature is the tuning dial governing the output. Lower it, and you get strict, unyielding logic. Raise it, and you introduce the mechanical chaos that humans interpret as creativity. With the probabilities locked in, the computer rolls the dice, samples the softmax distribution, and selects a single token. That new token is printed on your screen and immediately appended to the very end of your original input text. Then, the loop closes. The system grabs that newly updated passage, drops it back into the embedding matrix, and sends it through the exact same sequence to predict the word that comes after that. Every single time a new word appears in your chat window, the network has executed billions of matrix multiplications from scratch. The intelligence you observe is a flawless mechanical illusion. It is the result of fracturing discrete language into precise geometry, filtering it through static weights, and rigorously sampling the statistics, one token at a time.